De Burcht. We have an exciting program tonight with two speakers speaking about galaxies, both Sarah and Anniek. So for those of you who don't know, Astronomy on Tap has been going for a number of years, 7, let me get my maths right. There's about 40 locations all over the world. Unfortunately, most of them right now are either not running or doing an online event. And here in Leiden, we've been going since 2017, so several years already. You've probably already seen this because you've made it here to see us, but we have a YouTube channel. We usually put our videos up online afterwards. This time they're being streamed. You can find us online. We're on Facebook, Twitter, Instagram, all the cool stuff. So you're already here, you've already noticed, chairs are pretty far apart. We just ask you to done a great job already since you arrived to just try and keep it to the 1.5 meter separation, unless you're already in pairs or something. You will already probably have noticed that the bar is pen only, so unfortunately no cash. And just try and avoid mingling around too much and just take note when you leave, not to all rush the door at the same time. And for those of you hopefully listening in online, I'll check in a minute if you're actually able to hear any of this. We will take questions after the talk, preferentially from the room, because that's just easier. But if there are any questions from online, we'll try to ask them. Okay, first up, we have a little bit of astronomy news. Some exciting good things have been happening in the world. Well, maybe this is not in the world, it's leaving the world. Back on the 30th of July, so right at the end of last month, an FS5 rocket launched carrying the Perseverance rover to Mars. Some of you may remember several iterations of rovers that have been living on Mars for the last few years. So Perseverance is the next one. Some pretty cool numbers. It's currently traveling at 120 kilometers an hour. It's 10 million miles from the Earth already, just about 10 million kilometers from the Earth already, just in a month. And it's got 65 million kilometers to go, and hopefully in February next year, it'll land on Mars. Another really cool thing, very astronomy-specific news that happened recently, and quite relevant to tonight's talks. There's this really cool image of this ring of fire. This was taken by the ALMA telescope, it's a radio telescope. And it doesn't really look like a galaxy, but you may have come across and heard about gravitational lensing. We've had talks on this before. So this galaxy is actually lensed by another galaxy, so its shape gets a bit distorted. And it also gets brighter, so we're able to see it. So by some clever reconstructions, the image on the right is what we think this galaxy actually looks like. And the weird thing is that it's really, really far away. You'll hear Anniek talk about some of this kind of work too, looking at galaxies early in the age of the universe. The weird thing is that this galaxy is a lot like our Milky Way galaxy. It's a big disk. It's got gas spinning around, which is actually a little weird for galaxies early in the age of the universe. So that was a cool science result. So tonight we have two speakers. First up we have Anniek Gloudemans. Sorry about my Dutch pronunciation. Talking about the most distant galaxies in the universe. We'll have the quiz. And just a note about the quiz. So everybody in the room here, you have your answer sheets. And people online will hopefully share a link to the Google Answers. And then you can fill in the answers online as we go. Hopefully this will work. This is the first time we're testing this out. And just a note, there will be two sets of prizes. Prizes for those of you in the room, and prizes for those of you online. And in both of these, you'll have the two categories of, if you're an astronomer, that means you might know some of the answers already. And if you're a non-astronomer, so there's two categories, two chances to win. Then we'll have a short break, give you an opportunity to get a drink. Those at home also to get a drink. And then we'll go on to Sarah Leslie's talk, talking a little bit more about statistics of galaxy populations. Then we just kind of wrap up after that. So I'm going to very briefly introduce the two speakers before they both speak to avoid a little bit too much of switching around the computer, just to keep things a bit stable tonight. So first up we have Anniek. Anniek is a PhD student here at Leiden University in the observatory. They're actually both in the same group that I work in. So Anniek has a passion for observing and working particularly with observational data from a variety of different telescopes. And what she tries to do is find the most distant galaxies with strong radio emission. And a cool thing about Anniek is that she really likes stones, rocks. And you can see her here with a lovely gemstone. I don't know what those things are called, actually. So maybe in another life, Anniek would have been a geologist, but instead she likes stars and galaxies. They're pretty, so she's an astronomer. Our second speaker will be Sarah Leslie, and you see this same picture again. Sarah is a research fellow, well, again at Leiden Observatory, also in my group. She has, she works on studying how galaxies form, how they evolve, and how they grow. The problem is this takes millions of years. You can't sit back and wait for a galaxy to grow and evolve. They'll be dead. So instead, she studies large populations and tries to understand how they evolve. And a fun fact about Sarah is that she loves galaxies. She also likes art. She likes to paint galaxies. And also the moon. So that's a painting she made of the moon. And the picture on the left is a painting she made of the radio galaxy. And that is on the door of her and Anniek's office. So, whoops, sorry. We won't be back in a few minutes. First up, we have Anniek. So,
Thank you very much, Wendy, for this nice introduction. And I'm very happy to be here tonight with all of you and be able to give a talk together with my office mate, Sarah. And I hope tonight we will be able to give you an overview of observing galaxies. And in my talk, I will be focusing on observing the most distant galaxies in our universe. And then Sarah will take over and talk about how those distant galaxies evolve over time and how they evolve into the galaxies that we now know today. And we also live in today, of course. So before I start, I just want to say a big thank you to my supervisors and collaborators who put today in open. So it is only fitting to start this story at the very beginning, the very beginning of everything, namely the Big Bang. So here you see an overview of how we think this universe came to be. So we start here on the left, here, with a Big Bang. And just after the Big Bang, the universe is very small. It's a very hot plasma, meaning that all the hydrogen and helium that was formed is all ionized. And that means that it's all stripped of their electrons because it's so hot and dense. And shortly after the Big Bang, only a mere fraction of a second, it starts to inflate. And that means it starts expanding really fast. And this expansion actually causes the plasma to cool down. And as you can see, for the next phase of the universe's start, that takes a couple of years, about 400,000 years. But at this point, the universe is actually cooled enough for the hydrogen to become neutral again. So this means that the electrons come back to the proton and the neutral hydrogen atom is formed again. And from this point in time, we can see the very first light of our universe. And this we call the afterglow light pattern, or also called the cosmic microwave background. So here you see this very nice image made by the NASA satellite Planck. And here you see the temperature fluctuations in this very first primordial light. So after this period, the universe enters a very boring stage called the Dark Ages. And as you maybe can already imagine, in the Dark Ages, there's nothing really exciting happening. The universe is dark, there's no new light being formed yet, and we cannot really see anything. And this actually also takes quite a long time. Because after about 500 million years, the first stars and galaxies start to form. So this is a very, very important transition of our universe. And this transition, where the first stars and galaxies start to form, they actually start reionizing our universe. So here at this afterglow light pattern, we had neutral hydrogen, but now when the first galaxies started to form, they started reionizing their universe. So here in this image, all these tiny dots I show you here, those are actually galaxies, and around them they start forming these ionizing bubbles until the universe is almost completely ionized again. So this we call the epoch of reionization. And this is the second major transition in our universe, but we don't actually know a lot about this. We know this happened, and we know the rough time frame it happened, but we don't know exactly when it started, we don't know exactly when it ended, and we also don't really know what galaxies caused this. Was it maybe some massive galaxies that caused it, or was it many small galaxies that caused it? So there's still a lot of open questions here. And from this epoch of reionization, the galaxy or the universe actually started to form the structure as we now know it today. So in this beautiful simulation by the Team G collaboration, you can see the large-scale structure in the universe forming over time. And this large-scale structure is what we call the cosmic web. So maybe you can also see it kind of looks like a web. So here, in these very dense points, you have lots of galaxies forming. And between the points, they're all connected by these tiny strings, which we call filaments. And together, they make the universe how we know it today. So now, on Earth, if we use a very good telescope and we look at a very dark patch of the sky for a very, very long time, you get an image like this. And maybe you already noticed that this was also on my introduction slide, and that is because I think this is maybe one of the most beautiful astronomical images ever made by the Hubble Space Telescope. And this specific field is called the Hubble Ultra Deep Field. And all these little points and blobs that you see here in the image, those are not stars. Those are actually individual galaxies. Well, except for this one. That's a star. But all the other ones, they are galaxies. Well, you can see that they come in all these different kinds and shapes. And you see, for instance, this one is really big, and you can actually see its spiral arms. And this one is actually a very nearby galaxy. But you can also see, like once you start staring at this image and even zooming in, there's plenty of very, very tiny small dots. And some of those are very distant galaxies. And these galaxies are super interesting to study because when you look at a very distant galaxy, you're actually looking back in time. And that is because the speed of light is finite. So for the galaxy light to reach us here on Earth, it needs time to travel. So if we look at a galaxy that is 10 billion years away from us, we actually see it how it was 10 billion years ago. So we can use these galaxies as some kind of a time machine and look back in time and see how our very primordial universe looked like. And me specifically and my collaborators are interested in a specific type of distant galaxy, and those are called radio galaxies. So this is, I think, probably also the most pretty image of a radio galaxy. This is Hercules A, and this is actually a composite of two different images. So here, the background image you see here is again a Hubble image in the optical, and then overlaying there's a radio image made by the Very Large Array. So here in the red is how the galaxy looks like in radio. So what's happening here in this type of galaxy is that there's a supermassive black hole at the center of this galaxy, and mass is accreting onto it. And due to this very strong magnetic field, these jets are being formed and stuff is being flown out of the galaxy, forming these lobes. So these sources are super interesting to study. Well, first of all, because these supermassive black holes, we don't exactly yet know how those were formed. So studying these sources can learn us a lot about those. Also, the radio galaxies are the most massive galaxies at early times. and will also grow out to be the most massive galaxies in our universe today, in our local universe. So that makes them super interesting objects. And a very important one is that we can use them to measure 21 centimeter radiation from the epoch of reionization. So what is this 21 centimeter radiation? So here you see a small cartoon of a hydrogen atom. And so this hydrogen atom has a proton here in the center, an electron in its orbit around it. And when this electron flips a spin from up to down, it releases a photon with a wavelength of 21 centimeter. So when we detect this radiation, that is actually a direct detection of neutral hydrogen. And then my final point is that we know of a lot of radio galaxies, but we have not yet observed a radio galaxy further away than a redshift of 6. And you might be wondering, what is redshift? So for this, I have my lovely assistant. So we have this balloon. Sarah has this balloon. And on the balloon, there's a couple of points. Those are galaxies. And between the galaxies, we have these photons going around. But then, in the early time, the universe was small, but at some point it started expanding. So maybe you guys can see what's happening to these photons. So the photons, they're blowing up, just like what's happening in our very own universe. So this wavelength here, it's actually being stretched. So the wavelength is going longer, and it's becoming redder and redder. So thank you very much. And this lovely demonstration, we can actually put this down in a very elegant formula, which states that the observed wavelength divided by the emitted wavelength is equal to the radius or the size of the universe now divided by the size of the universe when it was emitted, and this is equal to 1 plus the redshift. So this means that when we talk about a redshift of 6, then we're talking about a distance when the universe was only 1/7 of the size that it is today. So that's very, very far away, as you can maybe imagine. And why would we even use this redshift instead of just talking about distances? Well, that is because to talk about the distance, you have to assume a cosmological model. You have to assume how fast the universe was expanding and when. And we don't really want to do this. We just want to be able to measure something that's just very exact. And this redshift will just give us this exact measurement. So astronomers talking about distance always talk about redshift. And when we're looking for very distant galaxies, we're talking about high redshift galaxies. So this is also very important for our 21 centimeter radiation, because at a redshift of 6, this 21 centimeter actually becomes 2 meters when we observe it here on Earth. So we need a very low frequency radio telescope to be able to measure this. And luckily we have one. It's called LOFAR. It stands for the Low Frequency Array. And its main core is actually located here in the Netherlands, somewhere in the area of Groningen. And here I show you a picture of this core station. And it's an aerial view. It's actually a very large area. And all these tiny dots you see here, and all these squares you see here, those are all individual antennas. And all these antennas together are precision, but they made it work, so yeah.
You say that after the Dark Ages, the universe is almost completely reionized. Is this an empirical fact? And, what observation is this based on?
Okay, so the question is, what observation is it based on that the universe is reionized again? So there's many different observations that prove this. So what people, for instance, do is looking at different sidelines to galaxies, and then you can measure how ionized it is. I don't think, okay, so it's very hard to constrain the precise amount of ionization, but you have these different methods you can use. Most of them, though, are indirect. So that is indeed difficult, but simulations such as the TMB simulation, they have also shown that this reionization process is definitely happening. So I don't think there's any doubt that it will or will not happen. It's just very hard still to constrain the precise amount and also when exactly this happens. Any questions?
You were talking about the radio galaxy at the beginning with the image of the galaxy with two jets of something coming out at the side. So those, when you're looking for these galaxies, are you looking for the signal from those jets specifically?
Not specifically, but the jets are indeed the thing that produces the radio emission.
Right.
So when we're looking at those very, very distant galaxies, maybe you can imagine that you won't be able to resolve the jets because it's just too far away, but you will just see a blob.
Yeah. So, but they look quite directional in a way. So does it matter somewhat if they point towards us?
Yeah, definitely. Yeah. So when they point towards us, we will see a stronger radio emission than when they point like exactly away from us. Yeah, definitely. So this is also a very large research area, alignment of radio jets. And actually also maybe you know that in astronomy you have these many different subclasses of everything. And also for radio galaxies, it's a big problem. How do we know if something is a different class or maybe the orientation is just different? So that's a very good point. Yeah. Any other questions?
Yeah. After the Big Bang, the universe is expanding. I don't know if everything is moving at the same speed towards each other. But if you have this radio galaxy, or I call it a gyroscope effect, if something is moving with speed on its own, its total speed is different as well. Is that affecting any of the results or the research, or how certain objects are moving opposite each other?
Okay, so I guess the question is about if the expansion of the universe will affect the motions of the individual galaxies.
Yes.
And the distances. Yes, but generally when you talk about the expansion of the universe, you're talking about a really large scale. So of course, most galaxies actually live in galaxy clusters nowadays. And that means that they live in tiny groups. And within those groups, they might actually not be moving away from us, but they actually might be moving towards you. But then if you look at a way larger scale, then everything will be moving away. So it really depends on what kind of scale you're looking for, but then for the distant radio galaxies I'm looking at, those will definitely be moving away because the structure is so large and it's so far away. Yeah, but I think also Sarah in her talk is gonna tell you a little bit more also about this. So.
A bit of a basic question, but you talk about inflation just after the Big Bang, and then the universe is expanding. Is that the same kind of phenomenon, or is it something different?
Okay, that's kind of a tough question. So the answer, the question was if the inflation is different than the expansion after the inflation. And yes, it definitely is different, but I cannot tell you exactly what, physically is happening there, because the inflation, that's a really ongoing area of research. We know an inflation must have happened to explain some of our observations. So for instance, to be able to explain the cosmic microwave background that we see, and the uniformity of our universe, and also the fact that our universe is almost completely flat, we need to assume that we had a period of inflation. Yeah, but when you do all the calculations, the mathematics, you do actually also end up with the inflation stopping at some point, and then just going on to a forever expansion of our universe. Yeah, so I hope that answers your question.
So maybe at a lower speed. Is that what you're saying?
Yes, definitely, definitely. So inflation is this gigantic, enormous expansion, and the expansion that we have right now is a lot slower than inflation.
Thank you.
Yes.
I think I have time for one more question.
I need two small questions. I just recently saw I recently saw an image on the internet like a couple of days ago. It was about the Big Bang also. It was a pretty like first was a bubble that contracted a little bit, and then the Big Bang came. Did you see that image?
No, I haven't. Was this a simulation, I guess?
Yeah, it was like a sort of simulation.
Or I thought maybe it was like an artist impression, or was it?
There was a theory behind it, so we had like let's say, used to that hole, and there were like a boost about contracted, then back out. So first there was something, then there was nothing to compress, and then
The only thing that this reminds me of is a theory called the Big Bounce.
Yeah.
And that is that the universe was created with the Big Bang, and at some point all the matter became very dense again, and it was crushed together in a ball again until it inflated again.
that's sort of.
So that theory is called like the Big Bounce theory.
Yeah, but if you see something thing about it, so it showed that small short particles was last week was about it. I don't have the English word was but and one more small question.
Yeah.
We have this in Dutch, you can send to Zenit magazine.
Sorry, again?
The Zenit magazine about astronomy, know about it?
Yeah.
Yeah, you put this in the Dutch and send it to the magazine.
Oh, you want me to? You mean write an article?
Yeah, and send it to us, so we can.
Oh, you're from the magazine.
Well, I know that.
Okay. Yeah, cool, sure. I actually also wrote some articles for the Dutch Journal of Physics.
Yes, nice. Send it also actually astronomy.
Yeah.
Yeah.
Cool. Okay, thanks guys.
So I saw some people in the bathroom, but hopefully they're very back before the actual game starts. So today we have 2 games for you. And as Wendy previously said, everybody in this room will do it on the papers. As you see, we have distributed them everywhere. And people watching through the YouTube stream can use this link here, or it should have also been posted in the YouTube chat. If you check it out, then you should be able to find it. So on the paper, you can do it with multiple people and you game together, and Corona allows you to be closer than 1.5 meters, so from the same household. And so please write a team name, whether it's your name or your team, and also write down if you are have astronomer in your team or not, because as Wendy said, we have 2 different kinds of prizes today. So 2 winners here and 2 winners online. Yeah? Everybody ready? Can I if you're ready, okay.
It doesn't work.
There you go.
Still doesn't work.
It will be from here then.
Oh, okay. Okay. Right. Sorry, I have to be here next to this. So if I block anything, please let me know. So first game, it is called Match the Galaxy. So the whole point is, can you match the optical galaxy to its H alpha counterpart? I will explain what this is all about in the next few slides. So here you see the spectrum of the light.
we have on this edge more short wavelengths and there longer wavelengths. And our visible spectrum is here. So this is an example of what a galaxy in optical light would look like. And then compared to, I am in a way, I don't know, okay, yeah. And compared to this, H alpha is only this little part of the optical spectrum, and this is what the H alpha galaxy, the same galaxy would look like in this wavelength. And H alpha is extremely useful because astronomers often use it to probe the star forming regions of the galaxy. I wish, but it's right. So this is the comparison that we are talking about. Can you find, if we give you the optical galaxy, can you find its counterpart in H alpha? So let's start. The first question, let me know if I'm in the way. I am. Right. So here we have an example of an optical galaxy, and you have to find A, B, or C, which is the H alpha counterpart.
Okay, can you just move the mic a little bit further from your mouth? Okay. Yeah, that's good. It's just a bit.
Okay, I think I can move on. I hope. Second one. Again, the same deal. We have a galaxy observed in the optical, and then in H alpha. Which one do you think is the correct one? Okay, moving on. Number 3, same deal. Okay, moving on again. Number 4. Yes, same orientation. Moving on. Number 5. All right, moving on again. No? Yes. Don't worry, there won't be endless. There's only going to be 8 of these. Yeah, right? Okay, next one. And the final one. Okay, guys, I've heard that there's a mistake in the form, and there's actually two number one answers in the paper form only, not the ones online. So I think you can just cross out the choose one. Exactly. Just choose one of the ones, and when I'm done through the second game, we can go through this again, so you make sure that all your questions are right and they haven't shifted really. Is that okay?
Yeah.
Cool. Okay. Just make sure that you know which one of the ones you answered. Okay. Game number 2. So this one is a bit different from the one we just did, where you have to mark A, B, C, and you just look at pictures. Instead, we now go on to crazy observing stories, whether they're real or made up. So I will be reading to you from a storybook, a few stories, and you will have to guess if they're real or if we have made them up. Right? I'm going here, just so nobody can see. No, but I can't because I have this. Right. The telescope that went missing. So this telescope went missing during its transportation. The trucker that was supposed to be transporting the telescope simply disappeared over the weekend, along with the telescope and the truck. After days of searching, the driver was found sleeping in the truck. But the telescope and the trailer that it was supposed to be in was nowhere to be seen. So, also the driver was absolutely useless. He didn't have any information about the telescope, and so the search for the telescope continued. The researchers who worked on this were obviously starting to get a bit panicked. After another day of searching, the trailer was finally found. The telescope was found to be undamaged. But the 2 bicycles that are also transported in this trailer were missing. Okay, moving on to the second story. Yeah, penguins came into the control room of the South Pole telescope. Yeah, that should say South Pole then. So, ever since the South Pole telescope saw first light in 2007, the astronomers have been making friends with the local penguins. As the penguins got used to the human presence, they grew less and less scared and more curious. So it happened one day that a penguin was found under the desk in the observatory control room. The crew guessed that the penguin had probably slipped in through the break room door, left open by a careless researcher, and then found its way into the control room, which was adjacent to the break room. Okay, moving on. So W first is a former spy telescope, and the story goes: the National Reconnaissance Office in the US offered NASA 2 second-hand telescopes built as spy telescopes originally. The next planned mission for NASA was the Wide Field Infrared Survey Telescope, or WFIRST. So the spy telescopes are used for the currently in development WFIRST mission. Okay, we move on. 4, bullets fired at a telescope. So the telescope you see here is in Texas, and it was a victim of vandalism. A worker at the observatory had a mental breakdown, and after firing a shot at the supervisor, he also shot multiple shots at the primary mirror of this telescope. He was probably hoping to shatter it, however it didn't shatter, so he went at it also with a hammer.
Where was that? Texas?
Yes. Okay, next. So, the Stratospheric Observatory for Infrared Astronomy, or SOFIA as we call it, is a telescope that is based in an airplane. In 2011, SOFIA went up for an observation run. After about half an hour in the air, the airplane experienced some pretty harsh turbulence, and the crew decided that they will abort the observations and change the course. But unfortunately, the telescope had already been damaged. The coolant had started leaking and had damaged the hardware of the telescope. All right, next one. So, the famous exoplanet system TRAPPIST-1 was discovered by 3 Belgian astronomers in 2015. They were observing at the Isaac Newton telescope in La Palma for 5 nights in a row. And due to bad weather, had to wait for about half the night for the skies to clear. To kill time, they decided to have some TRAPPIST spheres, which they had brought with them to the observatory. When later that night they discovered the 7th exoplanet system, they named it TRAPPIST after their beloved beer. Okay, and then final question or final story. Yeah, so the key scenes of a James Bond movie called Quantum of Solace were filmed at Paradal, the home of European Southern Observatory's Very Large Telescope that Anniek mentioned earlier. The site for the Very Large Telescope is a 2,600 meter high mountain that is in Atacama Desert in Chile. And the filming crew, which were about 300 people, had to travel every morning about 2 hours to get to the top of the hill for their filming, top of the mountain for their filming. Okay, I'm gonna go now through the first question really quickly, so you guys can check your answers. I should also say that, yeah, sorry, keep the papers because you will also be marking them. We don't want to go around collecting them, so you keep a hold of them, and we will correct them together after the second talk. Okay? So okay, let's go through these quickly. And let's go through this after Jordan. And finally, I forgot about this one. There's a tiebreaker as well that ties back to Anniek's talk. What is the ratio of the furthest known galaxy? This will be only used if you teams have the same results. Right, and now we have a 15-minute break. So until 25 past? Okay, yeah, 15-minute break, guys. And keep a hold of your sheets because we will check them later. We're gonna start again. So sorry to not get Mike to introduce Sarah, but I get her introduction area, so I'm just gonna pass it on to Sarah. Yeah. Okay. Maybe that's loud enough. Give us a shout if it's not. So thanks everyone for coming. I'm Sarah Leslie. I'm a postdoc at Leiden Observatory. And today I'm going to talk about unveiling the mysteries and histories of galaxies using the Cosmos Survey. And this is mostly work that I did during my PhD. I joined the Cosmos Survey during my PhD, which I did in Heidelberg in Germany at the Max Planck Institute for Astronomy. Okay, so galaxies are these beautiful structures that have stars and gas and dust and dark matter and black holes. And so we want to understand them better. Of course, we live in a galaxy, the Milky Way. This is a spiral galaxy, but it's not our galaxy. We live in the plane of the disk of our galaxy, so we can't get this nice bird's eye view. But if we could, it would look something like this. We live on the Orion spur, which is called the local arm of the Milky Way. So galaxies are these beautiful and mysterious objects, and we want to understand them better. So the Cosmos Survey, what is Cosmos? Unfortunately, sorry to disappoint you, I'm not talking about the TV show today. I'm talking about the Cosmos Survey, which is an abbreviation for the Cosmic Evolution Survey. And behind the survey, there's a lot of people. And in the Cosmos collaboration, we have over 100 scientists working from 12 different countries over 4 continents. And we work together because, well, telescopes are big and expensive instruments to build, so we all need to pull together our funding.
We also need to share our expertise. And so by sharing our time and our expertise, we can do the best possible science. And we like to meet about once a year. So this was a team photo taken in 2017 at our annual meeting in Kyoto. So that was the 14th Cosmos team meeting. So you can see that this collaboration has existed for quite some time now. And it's still going strong with, as I said, over 100 members. And I'll tell you a bit more about what we do in a moment. But you can see me at the back here. Next to, yeah. Okay, so the survey started with the Hubble Space Telescope. So after it was launched in 1990, well, and it had some problems with the mirror, and so then in 1993, luckily we were able to go and service it, put some glasses, and it started taking the most beautiful images. I'm sure you've seen many beautiful images from the Hubble Space Telescope. Oh, and also my earrings are 3D printed HSD. So, and it's a really cool instrument, and it inspired surveys like the Hubble Ultra Deep Field that Anniek showed us. So this was when astronomers decided, let's stare at a blank patch of the sky for hundreds of hours. So this was done over 25 days, which was 400 orbits of the Hubble Space Telescope around the Earth. And they observed this field in 4 different filters, so they could make this beautiful colored image. Now, this patch of sky has around 10,000 galaxies. But how do we know that this patch of sky is not just some special part of the universe? Is it a representative sample of galaxies in the universe? So this is where cosmos comes in. So the cosmos field is a much larger area. And so here you can see the area of cosmos, which is about 9 times the size of the moon, compared to the Hubble Ultra Deep Field, which is the small square here. And these other outlines show other Hubble Space Telescope surveys. So the cosmos field is the largest patch of sky that's been observed with the Hubble Space Telescope. And so it's not quite as deep as the Hubble Ultra Deep Field, but it was observed with 640 orbits using the advanced camera surveys. And it's still very deep. You can see each of these little spots, if you zoom in, is a galaxy. And in fact, this field was so large that it inspired our artist in residence, Carl Nell, who's based in South Africa, to commission some artwork. So Carl is a member of our collaboration. We're a very special collaboration. We have a resident artist who comes to all our meetings and takes notes and gives presentations as well. So it's a great part of science and art working together. Okay, so back to galaxies. You can see that galaxies today have a range of different shapes and colors and sizes. So on the right we have, the left, there's elliptical galaxies, which look a bit like a football, and they tend to be rounder in shape. Whereas we also have spiral galaxies, which tend to be flat like a disc. And there are some spiral galaxies which have bars, fortunately for us. The Milky Way has a bar, so we can drink beer. And then there are irregular galaxies, which don't fit into any of these nice classes. So this is a fly-through of the Gamma survey. So these are real images of galaxies that have been placed at different distances. And you can see that they, as we've mentioned before, the galaxies come in many different colors and shapes and sizes. You can also see that some galaxies live close to other galaxies, so they live in groups or clusters, and other galaxies live off on their own, like in the voids. And so we want to know, how did these structures and differences come to be, and how have galaxies changed over time? Now, as we mentioned before, that these changes of galaxies occur over millions of years, and we can't observe this in our lifetime. But fortunately, the universe acts as a time machine where when we look back further to the distant galaxies at high redshift, we're seeing them as they were in the universe. So seeing younger galaxies. And we can try to put these together as a picture of how galaxies have changed over the course of the universe or over the cosmic time. So just like archaeologists dig deeper into the earth to find fossils from earlier times, we astronomers look for fainter galaxies at higher redshift to see how the universe was at earlier times. And so this field is we call galaxy evolution, and it is one of the main reasons for conducting the Cosmos survey. But we didn't just stop with Hubble. We wanted to look at all different wavelengths, because looking at the world in different wavelengths gives us different information. So if we look, for example, in visible light at this adorable puppy, well, we can see that's an adorable puppy. But if instead our eyes were sensitive to infrared emission, we would see the temperature of the puppy. And I'm not a vet, so I'm not sure, but I think this shows that this is a very healthy puppy. He has a nice cold nose. But similarly, we can look at galaxies at different wavelengths. So this is our own Milky Way at visible wavelengths. So maybe not what we'd see with our eyes, but with a telescope. And you can see the stars, and the pink regions are the like what we were looking at before with the H alpha maps. That's where there's lots of young, recent star formation activity. And you can see these dark patches, which are dust lanes. So there's dust in between us and the stars that are absorbing the starlight. So we can't see through them. But if we look at infrared wavelengths, we can start to see the dust, because the dust gets heated by the starlight to temperatures that emit that we can see at infrared wavelengths. And then if we look at radio wavelengths, we can see all the way through the galaxy. So, yeah, so looking at different wavelengths is very useful to get the full picture of the galaxy. So, just to summarize, the optical light, which we see with our eyes, often traces stars, like our own star. And we can use space or ground-based telescopes like Hubble to observe galaxies in visible light. We have infrared radiation, which traces the dust component of galaxies. And we have to observe this with space-based telescopes like Herschel or Spitzer. At the shorter wavelengths, we're tracing very energetic phenomena like very hot gas or supermassive black holes. And we observe these with Chandra Space Telescope, amongst others. And as we heard earlier today, at long wavelengths we're sensitive to which is the radio regime. We're looking at often these beautiful jets that the supermassive black hole can produce. Okay. And we observe these with telescope arrays on the ground, like the Very Large Array, or LOFAR. So this is the Cosmos field. I'm going to show you in a few different wavelengths, but we basically try to use every telescope that we can and observe this field so that we get as much information as possible. So this is the field in visible light. This is what it looks like in infrared, X-ray, and this is the radio image. So this is actually an image that I worked on during my PhD, and it was done with the Very Large Array in New Mexico. It's a radio image. And if you zoom in on some of these points, you can see these beautiful radio jets, these radio galaxies from the supermassive black holes. But not all the radio emission is coming from, or in galaxies, comes from just these radio lobes. There's also another process that can produce radio emission. So here on the left is a picture of a supernova remnant. So when a massive star dies, they have fairly short lifetimes of only a few million years, which in the scheme of galaxies is a fairly short amount of time. So when a massive star dies, it goes supernova, And these supernovae produce shocks as it expands out into its surroundings. And these shocks accelerate particles like electrons to very fast speeds. So, and then these relativistic electrons, as they're moving through the galaxy and spiraling around the magnetic fields of the galaxy, they produce a type of radiation called synchrotron radiation, which is what we can observe with our radio telescopes. So by looking at these supernova events, which traces when the star dies, I'm in a way tracing how many stars have been born. So I'm using the death rate to trace the birth rate of massive stars in galaxies. So I'm looking, so what I did was using the radio emission in the cosmos field to trace the rate at which stars are forming in galaxies. And this is a figure from my work, which I will explain. So on the y-axis, it shows the rate of star formation. So how many stars are being born every year. And on the x-axis is the stellar mass. So more massive galaxies are over here on the right. And in the purple line, it shows the average relation. So if I took all the galaxies in the cosmos field at this particular redshift, so all the galaxies that lived around 4 billion years ago, you can see that the most massive galaxies are forming stars the fastest. Then I also split galaxies based on their shapes. So I found irregular galaxies have a fairly high star formation rate, and then spiral galaxies, which are the blue points, also have a fairly high star formation rate, but not quite as high as the irregulars. If I separated galaxies that were spiral but also have a bit of a bulge, which is like a central bright component, and they have a lower star formation. And then if there are any elliptical galaxies, they would have a lower star formation. And then if you look at higher redshifts, so this were galaxies, I'm seeing them how they were about 7 billion years ago. You can see on average, the average relation in the background is higher. So on average, galaxies were forming stars at a faster rate earlier on in the universe. But still the relation that the irregular galaxies are forming more stars every year compared to spiral galaxies, which are forming more stars compared to spiral, bulgy, and the elliptical galaxies. And then as you go to even higher redshifts, the measurements become a bit harder to make because galaxies are very small, and we're also, for a number of reasons, but they're also fainter, and so I have fewer data points here. But at around this redshift of redshift 1 is the time when our own Milky Way was forming its disk. So we know that galaxies can change their structure over time, and one of the ways that they can change their structure is through interactions with other galaxies. So our own Milky Way has had a few interactions in the past, but mostly with small galaxies. So it hasn't really changed the structure so much. But in the future, we're going to have a major merger with the Andromeda Galaxy, which is a similar mass to our own Milky Way. And so based on the current positions of these galaxies and their velocities, people can run computer simulations to project forwards into the future of what's going to happen. So you can see that the Milky Way and Andromeda are getting closer as gravity is pulling them together. Then they, after their first pass, gas and stars get redistributed. In fact, a lot of gas is going to get funneled in towards the center of the galaxy. You're going to have a lot of star formation, new stars being formed as the gas collides. And then after around 7 or 8 billion years, the two galaxies will coalesce into one system. So we'll have to come up with a new name, probably will be called Milkomeda. And then we're left with one of these elliptical red galaxies, black holes. So this is one of the ways that you can transform a spiral galaxy into an elliptical galaxy. And that's what's going to happen to us in the future. And if Earth is still around, this is what this process will look like from that. So if we could, so this is, for example, what the night sky looks like now, if you're very lucky. In 2 billion years, billion years, not 2 billion years, we can see the Andromeda approaching, and then as they crash together, there's huge amounts of stars being formed. That's sort of this pink, these are the ionizing bubbles that the star produces. And yeah, and then after around 7 years, we'll just be in a completely different looking galaxy. So I'm going to end here, but studying galaxy evolution is interesting not only for understanding how the Milky Way fits into the larger picture of galaxy populations, but also for working out what's going to happen to us in the future. And to study galaxy evolution, we need deep observations to detect the most distant galaxies because they're very faint. We want to look at a large area so that we can find rare objects like the radio galaxies Anniek talked about, and so that we can be sure that we've sampled a large enough sample that we're sure that we're representative and we can trust our conclusions. And we want to survey in all different wavelengths, because different wavelengths trace different components and different phenomena in the galaxies. And the Cosmos survey, Cosmos field, provides this kind of information. Thank you.
Thank you very much, Sarah. We have time for a few questions. If we just repeat them, so that the audience will know. Any questions?
Correct me if I'm wrong. So through your research, you can prove that we're getting less and less stars, right?
Yes.
What's the prediction for the future? 7 billion years from now on?
Yeah.
How many less stars we can have?
Yeah, so I like to look at the universe as a whole, and over time, the overall star formation. Actually, I think I might. No, I deleted the slide. I had a backup slide showing what was going to happen. Yeah, so over time, it takes galaxies a little bit of time to get going and really start forming their stars. And then there was a peak of star formation at around redshifts of 2 and 3, and this was a peak because the galaxies had a lot of fuel, so they had a lot of molecular gas from which stars form. And then over time, with recent observations, have started to show that the gas content of galaxies has been decreasing. So that could explain, in part, why the star formation rate of galaxies has been going down as we use up our fuel. Yeah. So in the future, there'll be even less stars being formed, and then we'll be even if we didn't merge with Andromeda, we'd end up being a fairly red-looking galaxy with just old stars. So older stars look red and younger stars look white. So it would be like a red galaxy. And I think that's what's going to happen to most galaxies in the end.
In the end.
In the end. And also, the universe is expanding, so galaxies are getting further and further away, so we're not going to be able to see nearby galaxies eventually. So we've got to do this stuff now. I'm just joking. This stuff takes billions of years. We've got time.
Any other positive questions?
That's positive. Yes.
Let's say well, bigger stars living at billions of years, if they explode more, you get more stars, of course, that will make more star systems.
Yeah, so the question, I think I forgot to repeat the previous question, but the question was, when the massive stars explode, does that trigger new episodes of star formation? And the answer is yes. I showed the supernova was pushing out material into its surroundings, and that compression can trigger new star systems to form.
Yeah. But still, because they are spreading more out, they in which you are starting to marry the new stars.
But yeah, so if you get, so it's still, I guess overall, you're not, you need, if you want to keep making new stars, you have to put in some new gas. But actually, no, that is a good point. So there seems to be some processes that are stopping some galaxies from forming stars, and we call this quenching. So one of these mechanisms could be, as you say, the supernova, if you get a lot of them occurring in the same region of the galaxy, you can have winds, and this can blow the material out of the galaxies. Although we think over time a lot of that material will be able to fall back onto the galaxy. The other interesting mechanism, one of the other interesting mechanisms that can cause gas to stop forming stars is AGN, which is the supermassive black holes. They can add heat to the surroundings, and if the gas is too hot, it can't form stars as well. So these are, this is very much an active field of research that I'm very interested in, understanding what's stopping galaxies from forming stars.
So starting with too hot, so we go to, let's say,
sorry, could you repeat?
So if the star gets too hot, don't go supernova? Or,
if a star gets too hot, it won't go supernova.
Because this star is not too hot for supernova, but the other stars,
So it's the most hottest stars that go supernova.
Yeah.
Actually, they're the most massive stars. And the other less massive stars just end their lives as white dwarfs.
Yeah.
So that's less interesting from my point of view, where I'm interested in what's affecting the galaxy on a whole. Okay, is there any other questions?
So you've shown that the more massive galaxies tend to form more stars.
Yes.
But also different shapes of galaxies tend to have different ways of forming stars. Does that have something to do with the geometry of it? Is there regions in each of these types of galaxies that form more stars than other regions? I don't know, towards the center or towards the arms, or is it just because of the age?
Yeah, so the question was about how I showed that not only do the more massive galaxies form stars at a faster rate, but also different galaxies with different shapes of forming stars, and is forming more stars. And is this due to the what is this due to? And I guess a part of the answer is, I think, the shape. But another key ingredient is the gas content, which I mentioned. So maybe these disk galaxies have more gas, and that actually helps them become disks, because the gas can dissipate under momentum, so they can form a disk. Whereas the elliptical kind of galaxies, they are more random motions. But that's a good question.
Maybe a stupid basic question. Are all the objects in space, are they caught in galaxies, or are there also often moving objects?
That's a great question. So the question was, are all the objects in space caught within galaxies, or is that something else? And actually, if you look at the baryon content of the universe, the type of matter that we're made of, a lot of it is actually we think is in very hot phase. That's not in galaxies. It's just a hot gas in between galaxies. There's a lot of material out there, but it's very hard to see that because it doesn't radiate at temperatures that we can see easily.
So will it be swallowed by nearby galaxies then, or just moving around on their own?
Yeah, I guess most material will be gravitationally affected by galaxies and go towards it, but because it's at this high temperature, it has its own pressure and its own way of doing things. So I don't know exactly how to answer your question. Yeah. I would have to look at the simulations.
Great, well, sorry. But thank you very much for a great talk.
Okay, so I wanted to first say that for the people watching online, that I have noted down the names of the teams that won there, and I will let you know when we have talked about the answers. So hold on a bit. Right, and for everybody here in this room, can you please mark along whether you got the correct answer or not when I give you the answers? And then on the second, on the other side of the paper, there's a line that says total points, so you can just write it there, and then we will have like a bit of a yelling session and see who won. No, it's fine. We will do it in a civilized manner. Okay, so are we going? No, it's not working again. Okay, cool. So the first game, the first question. I don't know, wait a bit. So A was the correct answer. Okay, moving on. Number 2. C was the correct answer. Moving on again. 3. C again. All right. Number 4. B. Number 5. A. Number 6. C. Number 7. A. And number 8. B. Okay, you didn't miss anything. You got your points for the first game. All good. Okay, cool. Let's go for our story part of the game then, because I have some more things to say about it. Right. Second game. You guys ready? So, this is exactly on top. Can we move it? Yeah. Thank you. So the first one is in Gabriel. This happened in 2012 to the researchers of the University of Minnesota. The telescope was supposed to be, it's kind of hinted here, was supposed to be going up on a balloon. And the cost was around $500,000, but this didn't include labor, and the researchers had worked on it for around 7 to 8 years. So it would have been really disastrous for them to have lost this telescope. And it doesn't work again. Press it, yeah. Second, the penguins. It's fake, unfortunately, although it's a very cute story. So I think we made it up. Right. And next one. The former spy telescope. This is a real thing that happened. The W-FIRST is planned to launch in 2025, and it is indeed the second-hand spy telescope. It is, however, unclear whether this donation to NASA is going to save NASA any money, because now that the telescope is donated to them, it is much bigger than they originally planned, so they still have to pay for a larger camera and a larger rocket to launch it. So still might be very expensive. 4, bullet in the telescope. This is a real event, and this happened at the Harlan J. Smith telescope in 1970. In total, 7 shots were fired at the telescope. You can see 6 of them here. So the holes had only a minor effect actually in the end on the quality of the telescope images. The holes slightly reduced the amount of light that the telescope could collect and introduced a very small amount of diffraction. However, since the effect is such a small thing, the telescope carried on with its observing program already the following night. Right, coolant. This is a fake story, although it's true that there is a telescope called Sophia on board of a plane. This story about the leaking coolant is fake, it's made up. The TRAPPIST system. This is also a fake story. So the TRAPPIST system is not named after the beer, it's named after the telescope it was discovered with. So it's called the Transiting Planets and Planetesimal Small Telescope, or TRAPPIST, at the La Silla Observatory in Chile. And final one. So this is a real thing. So the scenes are mostly filmed at the Parallel Residencia, which you see here on this picture. So this is the accommodation for the staff operating the very large telescope. And you can see the same thing here being blown up in the poster. So this is a real thing that happened. I think. Right, and then finally, the tiebreaker answer, the correct answer is 11.9. And Anniek mentioned earlier that the furthest galaxies that found in radio are around 6 redshift. Then the overall known galaxies are further because they can also be found in other wavelengths such as optic. So, can you tally up your scores? I didn't. Okay. let's do it in maybe a different way. How about if you have already calculated them? Maybe I can just ask if anybody got above 10. 1, 2, 3. I see. So, did any of you? Does any of you have astronomers? You guys do? No? No? Okay. So I guess we know who the astronomers were. How many points did you get? 12. Okay. And the other 2 teams, you got more than 10. Did you get more than 12? No? Okay. How many points did you get? 11. 11 as well. Okay. How about your tiebreaker? 9.2. You didn't do this? Okay, so we have our winners. One astronomers team there and another astronomers team. Prizes here for you guys. I didn't forget about the people online. They also have 2 winners. So the non-astronomer team who won with 11 points as well is called Team Sloth. So since you left your email, we will be sending you present after the event. And then we have an astronomers team who got 10 points called Team Galactose Tolerant. So congratulations to you two, and we will be contacting both of you after the event. Okay, guys, this is it for the games. Thank you so much. Thank you. Next month we hope to do this again, so hopefully we'll see you again.
as always, contingent on actual corona going well. We've yet to confirm our speakers, so we'll let you know as soon as possible. As always, look out online for other events. And briefly, just thank you to everybody in our team. Not everybody is able to be here tonight, but this wouldn't happen unless a lot of people put in some effort. And finally, tonight we're quite pleased to be able to present our glasses in real life to our two speakers. So thank you all for coming out tonight. Thank you for everybody who's been online.